of a source lamp, which is something as simple as the headlamp from a motor scooter, or more complicated like a deuterium lamp or xenon arc lamp. The next device in line is what's known as a monochromator, which is two slits which separate or are separated by a prism or a diffraction grating. The next element of our spectrophotometer is what's known as a beam splitter, which divides a beam of light into two equal parallel beams of light. Next is the sample compartment, which contains cells for both a reference and a sample. And finally, detectors, which are devices that convert the impact of photons into electrical current that can be monitored by a computer. So now that we've defined each of the smaller pieces within our spectrophotometer, let's turn it on and see what happens. I'll ignite the source lamp, creating a variety of wavelengths of different light. This light passes through the first slit of the monochromator, ensuring that all of those light photons are traveling along parallel pathways, so that when they strike the prism, they are refracted into a rainbow of colors. So each wavelength of light is moving to a different place in space. So only one wavelength of light in this situation is going to make it through the second slit in my monochromator, striking the beam splitter and becoming two beams of equal intensity. These two beams of equal intensity will traverse a cell, a different one for each of course, one being the reference and one being the sample cell. As the beam exits these cells, it strikes the detectors, which are firing away, creating an electrical current. And you'll notice at the moment that the intensity of the light exiting both the reference and sample cells is identical. Therefore, the current generated by each detector is identical. So in this case, the intensity detected by each of my two detectors are the same. So if I were to consider the ratio of the intensity leaving the sample cell to that leaving the reference cell, I see that the transmittance of my sample cell is 100% that of the reference. So I'm going to plot that here at 0 concentration, 100% transmittance. Now let's add a little sample to that cell, something that might absorb this light. Now notice that when I do this, the intensity of the light exiting the sample cell has decreased, and therefore the current generated by its detector has also decreased. So now the ratio of intensities is no longer 100%. In this case, let's say that it's down to 50% at a given concentration, which I'm going to call X. If I add another equivalent of my sample to the sample cell, that decreases the intensity even more. Not only that, it decreases the intensity at the sample cell by a known amount, exactly 1/2 for each equivalent of sample that I add. So when I compare my new intensities at the sample and reference cells, I see that I'm now at 25% transmittance. And similarly, an incremental increase in the concentration once more in my sample cell leads to another reduction by 50%, and therefore a percent transmittance of 12.5. Now we have enough data points to see something very interesting here. The relationship between the percent transmittance and the concentration of a sample is not linear. Instead, it's exponential. And while it's very useful to have this information, scientists and spectroscopists prefer, if they can, to discuss linear relationships within their data, because this makes for a much simpler discussion, and it's much easier to predict how things will behave if we have a simple linear plot to compare. This is where the Beer-Lambert law comes in. You'll notice that right now I have an exponential relationship between my percent transmittance and my concentration. We can see that in the equation here, where the concentration is a term up here in the exponent. But what August Beer did was to convert that percent transmittance into a new unit called absorbance. And he did so by taking the logarithm, or really the negative logarithm, of the transmittance. Taking the logarithm of an exponential function creates a linear function. And so the data, when plotted as absorbance rather than transmittance, is actually considerably easier to look at. Not to mention, it's much easier to predict the exact absorbance by either extrapolating or interpolating within the data set that I've collected. This is the utility of the Beer-Lambert law, and the reason why we convert percent transmittance into absorbance so often when conducting UV visible spectroscopy. That's all for now, everyone. I'm Professor Davis from ChemSurvival.com and the YouTube channel ChemSurvival. I'll see you on my next video. I'd like to thank everyone for making ChemSurvival.com and my YouTube channel ChemSurvival such a success. And I'd also like
Okay, anybody want to share from the videos, based on experience in the lab, okay, and then the videos, and then maybe something that maybe you read, is there anything that you want to share before, before I ask you? Or are you really, most of you, are you really understand, the subject? Right. I have to call your name, okay? No choice. Right, okay, Ahmad Faik Sayuti. Right, okay, I start with A, okay? So we have around about, how many of you here? Ada ke Faik Sayuti ni? Ke nama lain ni? Ahmad Faik Sayuti.
Faik tu KSF 1 iron dia.
Oh, ini the ini senarai overall. Right, okay, habis on ni lah. Right, okay. Amir Faizal Zulkarnain, okay. Amir Faizal? Amir Faizal, are you here?
Yes, doctor.
Okay, Amir. Okay, anything you want to share from the video?
Oh, sorry, doktor. Saya dari tandas tadi, doktor.
Kita tandas. Okay, tak apalah. Video tu ada berkaitan dengan UV visible, okay? UV visible spectroscopy. Anything you want to ask about UV visible spectroscopy?
UV visible.
Tahu tak UV visible tu guna untuk apa?
And absorbent.
Okay, absorbent tu apa?
Kadar penyerapan cahaya oleh molekul.
Yelah, and then apa what's the significance of it?
Significant.
You can relate that into your experiment, okay, in the lab. What's the significance of using absorption spectroscopy?
To know what's the content. What's the content?
Konten apa? Konten buku ke? Konten almari ke? Tak apa, yang dia share lagi sekali video. Okay, Amir Faizal tengok betul-betul and the rest of you. So Ayanda akan share sekali lagi video. Video ni penting. Ini to me this the best videos on the UV visible spectroscopy to understand the concept. Because they're having actually what they preparing here, okay, for this part. Okay, ni yang cursor Ayanda moving now. Okay, I'm moving now. Okay, actually this is actually the instrumentation part. The instrumentation part on how each component has been arranged, okay, in order for them, okay, to work and to be able, okay, to measure the amount of light, okay, that has been absorbed, by our sample. And then this video also is going to relate, the amount of light which have been absorbed, okay, with the concentration, okay. So they're going to have this concentration versus transmittance of light, okay? And then later on, okay, they convert transmitted into absorbance, all right? So please have a look. This very important videos, okay? The rest actually I'm not going to share, but the one actually, you can see them on your spare time. Okay, so please have a look again. Watch the video and enjoy your show.
Hey everybody, Professor Davis here from ChemSurvival.com and the YouTube channel ChemSurvival, and today I'm going to give you a brief introduction to UV visible spectroscopy and the Beer-Lambert law. To begin our discussion, I've drawn a schematic on the bottom half of this screen depicting a fairly typical setup for a UV visible spectrophotometer. Now there are many different ways to build a spectrophotometer, but this is one of the simpler designs, so I thought we'd start there. It consists of a source lamp, which is something as simple as the headlamp from a motor scooter, or more complicated like a deuterium lamp or xenon arc lamp. The next device in line is what's known as a monochromator, which is two slits which separate, or are separated by, a prism or a diffraction grating. The next element of our spectrophotometer is what's known as a beam splitter, which divides a beam of light into two equal parallel beams of light. Next is the sample compartment, which contains cells for both a reference and a sample. And finally, detectors, which are devices that convert the impact of photons into electrical current that can be monitored by a computer. So now that we've defined each of the smaller pieces within our spectrophotometer, let's turn it on and see what happens. I'll ignite the source lamp, creating a variety of wavelengths of different light. This light passes through the first slit of the monochromator, ensuring that all of those light photons are traveling along parallel pathways, so that when they strike the prism, they are refracted into a rainbow of colors. So each wavelength of light is moving to a different place in space. So only one wavelength of light in this situation is going to make it through the second slit in my monochromator, striking the beam splitter and becoming two beams of equal intensity. These two beams of equal intensity will traverse a cell, a different one for each of course, one being the reference and one being the sample cell. As the beam exits these cells, it strikes the detectors, which are firing away, creating an electrical current. And you'll notice at the moment that the intensity of the light exiting both the reference and sample cells is identical. Therefore, the current generated by each detector is identical. So in this case, the intensity detected by each of my two detectors are the same. So if I were to consider the ratio of the intensity leaving the sample cell to that leaving the reference cell, I see that the transmittance of my sample cell is 100% that of the reference. So I'm going to plot that here at 0 concentration, 100% transmittance. Now let's add a little sample to that cell, something that might absorb this light. Now notice that when I do this, the intensity of the light exiting the sample cell has decreased, and therefore the current generated by its detector has also decreased. So now the ratio of intensities is no longer 100%. In this case, let's say that it's down to 50% at a given concentration, which I'm going to call X. If I add another equivalent of my sample to the sample cell, that decreases the intensity even more. Not only that, it decreases the intensity at the sample cell by a known amount, exactly 1/2 for each equivalent of sample that I add. So when I compare my new intensities at the sample and reference cells, I see that I'm now at 25% transmittance. And similarly, an incremental increase in the concentration once more in my sample cell leads to another reduction by 50%, and therefore a percent transmittance of 12.5. Now we have enough data points to see something very interesting here. The relationship between the percent transmittance and the concentration of a sample is not linear. Instead, it's exponential. And while it's very useful to have this information, scientists and spectroscopists prefer, if they can, to discuss linear relationships within their data, because this makes for a much simpler discussion, and it's much easier to predict how things will behave if we have a simple linear plot to compare. This is where the Beer-Lambert law comes in. You'll notice that right now I have an exponential relationship between my percent transmittance and my concentration. We can see that in the equation here, where the concentration is a term up here in the exponent. But what August Beer did was to convert that percent transmittance into a new unit called absorbance. And he did so by taking the logarithm, or really the negative logarithm, of the transmittance. Taking the logarithm of an exponential function creates a linear function. And so the data, when plotted as absorbance rather than transmittance, is actually considerably easier to look at. Not to mention, it's much easier to predict the exact absorbance by either extrapolating or interpolating within the data set that I've collected. This is the utility of the Beer-Lambert law, and the reason why we convert percent transmittance into absorbance so often when conducting UV visible spectroscopy. That's all for now, everyone. I'm Professor Davis from ChemSurvival.com and the YouTube channel ChemSurvival. I'll see you on my next video. I'd like to thank everyone for making ChemSurvival.com and my YouTube channel ChemSurvival such a success. And I'd also like to invite you to check out a new project I've been working on coming in October 2014. It's a 36-part organic chemistry course developed in collaboration with the Great Courses. To get more information about my course.
Right, okay. Under Amir. I think quite clear now, isn't it? So,
Maybe.
so what's the thing that you learned, okay, from the video? Tell me.
From the video, we can see that the data that we get is transmitted of the sample.
Sorry, say it again. The what? The deduct?
The detector detect the transmission of light from the sample.
Okay.
And
Okay.
then to calculate the absorbance, we use negative log transmitted.
Okay. Why is it necessary for us to convert from transmittance, to absorbance? What's wrong with it? There's nothing wrong with transmittance, isn't it? Okay. So why should we convert from transmittance into absorbance? I mean,
Easier to understand.
sorry?
Easier to understand.
What to understand? Tak dengar awal tu.
Easier.
Easier to understand. Okay. Easier to understand. Why is easier to understand? What made absorbent is much easier for us to understand compared to transmittant? Okay.
Because we use UV spectrum.
Tadi dah okay lah. Balik spektrum tu dah out lah. Alright, okay. You kata convert, okay, they measure transmittance. Transmittance, and then we convert to minus log, okay, transmittant, okay, for the absorbance. And you said because it's very easier for us to understand. And then why do you think it's easier for us to understand if we measure in absorbance? You see, because of the spectrum. Oh, tu tak kena. Okay. Tu tak apa. Try once again. Okay. What makes absorbance is more convenient for us to measure compared to transmittance? Okay. Another. Amir?
I'm still thinking.
Okay, you keep thinking. Okay, well, I'm asking others, to what you call it? I mean, to continue, with what your argument. Okay, so I prefer Muhammad Aziz Lukman. Muhammad Aziz? Aziz Lukman, are you there?
Yes, I'm here, sir.
Okay, Aziz, sambung the argument from Amir just now. Why do we measure absorbance and not transmittance? Are you agree with it? I mean, is it absorbance more convenient than transmittance?
I'm agree with Ame.
You agree with Amir? Oh, bagus ni, sahabat setia. Okay, what make you agree with Amir? What make you think okay the absorbent actually more convenient? It's more comfortable, yeah, more convenient and much easier compared to if we measure transmittance.
Because the absorbent can detect the the light absorbed
Sama
by the
transmitter.
molecule.
Transmitter can also measure, no problem, because transmitter actually measuring the amount of light that's been transmitted. Okay. Supposedly siapa yang menjerit tu? Okay, supposedly you are having 100% light. Okay. And then what been transmitted actually say 50%. So you know that 50%, the remaining 50% actually has been absorbed. So even transmission, you can still assess the absorbance. Okay. Haziq. So what's your next guessing?
That guessing. I'm not agree. We have
Cis, ini tidak ada pendirian ini. Okay, so according to you, transmittance actually is more convenient compared to absorbance, is it?
no. Transmittance is equally convenient to the transmittant.
Equally convenient. Ini 100%. Okay, alright. Okay, at least that's your opinion, okay, and see whether it's right or wrong, okay. So can I have another say, another opinions, maybe from Nur Izian, Shahira?
Ayanda, can I try?
Oh, good Asfa. Okay, good Asfa. Okay, yep.
I think it is easier to use absorbance because it will give a linear graph.
Yes, that's the thing. Okay, so big clap, to Asfa. Tu je. Okay. Amir dan Muhammad Aziz. Amir correct, okay. Tapi argument tu tak memberasakan. Ini Aziz ni play safe ni. Alright. Okay. So tak apa, we learn from our mistake. So the reason, if you can, okay, if I show back, the video just now. Hilang dah video tu. Hilang dah video tu sekejap, ya.
Hey everybody, firing away, creating is 100 has add another and a half transmittance unit called a data set that I've collected. Considerably easier. And so the data, when plotted as absorbance rather than transmittance, is actually considerably easier. New unit called term up here in the now have an exponential relationship between my percent transmittance and my concentration. We can see that in the equation here, where the concentration is a term up here in the exponent. But what August Beer did was to convert that percent transmittance into a new unit called absorbance. And he did so by taking the logarithm, or really the negative logarithm, of the transmittance. Taking the logarithm of an exponential function creates a linear function. And so the data, when plotted as absorbance rather than transmittance, is actually considerably easier to look at. Not to mention, it's much easier to predict the exact absorbance by either extrapolating or interpolating within the data set that I've collected. This is the utility of the Beer-Lambert law, and the reason why we convert percent transmittance into absorbance so often when conducting UV visible spectroscopy.
Okay, another that's the answers. All right. So if you measure transmittance, okay, what you're going to have actually this is the expression. You need a formula, okay, that involved. Okay, so you're going to have a curvature. Curvature, exponential curvature. But if you like what Pakcik Bias and Lambert did, okay, so basically they introduced, you know, a new parameter called absorbance. And they define absorbance as minus log T. So once they replace this, they define and they replace this again to this equation. Okay. So I mean, as a result, again, they can simplify, you know, this equation and become like this. Absorbance equal to absorptivity, which is a constant. Okay, time concentration and time path length. Path length normally, you know, conventionally we agree path length will be set into 1.0 centimeter. So this actually is like, I mean, this relationship here is just like, you know, a straight line, y equivalent to m's x. M actually the slope. So here's the same thing. So this y absorbent, you know, the y-axis here equal to m, which is the slope, okay, the absorptivity. Okay, and length also, the length is also constant. So absorptivity and the length here, path length actually is constant. So the x actually the variable, actually concentration here. And when you plot graph, okay, we expect the graph is going to be a straight line like this. All right. Okay. So as we mentioned in the video just now, if you're having a straight line, it's much easier for you to do interpolation and extrapolation. All right. Another, what the difference between interpolation and extrapolation? Anybody want to guess? What the difference between interpolation and extrapolation? This is not chemistry. I'm asking you about the mathematical, you know, basic concept that you have learned, okay, during your secondary school. What is interpolation? Are you having a calibration graph? Okay, what do you mean by interpolation and extrapolation? Extrapolate and interpolate. What is different? Another? Because if you are having a straight line, okay, so we are able, you know, to determine confidently, you know, the equation, okay, that representing that straight line, yeah. By knowing the expression, by knowing the formula for the straight line, so supposedly if we have the unknown, okay, we're just simply taking the value of the unknown inside, you know, the expression, mathematical expression, and we should be able to determine the concentration. Okay, so as simple as that. Okay, but actually in this, I mean, in a curvature, it's a bit difficult. Okay, I mean for us, you know, to do the what you call the interpolation and extrapolation. Extrapolation could be not possible, but interpolation, okay, within the region, okay, might be possible, okay, but with certain degree of error, okay, because it's not straight line, okay. If not straight line, when you do the interpolation, you need to do the tangent, okay, into the hyperbolic, okay, because actually in exponential it's like hyperbolics. So once you want to do the interpolation at that particular point, you need to do, I mean, you know, select dotted line, and then once the dotted line actually reach, you know, the curvature, okay, so you need to draw the tangent, okay, the tangent line, okay, and then from that you're going to determine, okay, the what you call, you know, the concentration of the unknown. But okay, doing that, okay, it's going to incur, okay, certain error as well, okay. So it's going to more or less, okay, it's going to affect, you know, our data as well, okay. But with straight line, it's much easier for us to do. Okay, another, is that clear? Is that clear? So I just want to ask what the difference between interpolation and extrapolation. Okay, thank you, Faizal Amir. Okay, Fatin Nur Balkis, are you there? Fatin Nur Balkis?
Yes, Doctor.
Yes, okay. Fatin, what is the difference between interpolation and extrapolation? Have you done your UV visible lab? On the
Esok baru nak buat.
besok pun nak buat. Okay, baru nak buat. Alright, okay.
Mm-mm.
So what is interpolation and extrapolation? Pernah bikin graf sebelum ni?
Pernah.
Takkan tak pernah kan? Mestilah dia buat interpolation dan extrapolation. What is interpolation? What is extrapolation? Fatin.
Doktor, kalau nak kata boleh?
Ya, sure. Open to everybody. Okay. Okay, Daniel.
Extrapolation tu dia macam kita nak estimate apa graf yang bersambung selepas ni. Inter tu macam data yang kita plotkan dekat apa yang range yang kita dapat tu. Extra tu yang estimate after or before.
Yes. Okay, it's good. Congratulations, Daniel. All right. Okay, so big clap to him. So interpolation, okay, you interpolate. Okay, mana you determine, the data, the concentration, of the unknown, and that concentration actually within, okay, the concentration of the standard, okay, that you prepared. Once you establish, your calibration graph, okay, actually you prepare a set of solution, isn't it? Like your experiment in the lab, okay, you prepare, and then for the interpolation, okay, actually you use that graph, okay, to predict, the concentration of unknown within the concentration, okay, that we prepare. Supposedly, okay, contohnya, okay, we prepare from 0 ppm of copper, okay, for instance, okay, sampai say 500 ppm of copper. All right. So you put a graph and you get a very, very nice straight line. Yeah? And then you have an unknown. Okay, so you run. Okay, your unknown, of course, you need to determine the concentration of copper. Okay, for instance, inside. Okay, but you run, and once you run, okay, you notice that the absorbance at least within, okay, the highest absorbance that you achieve for your calibration and the lowest. Suppose the lowest is actually 0, and the highest supposedly adalah 1. Okay, so for your unknown, actually the absorbance within 0 and 1. So I mean the process of doing the interpolation and getting, the concentration of the unknown, okay, that is called interpolation. Extrapolation, again, when you try to determine, but the concentration actually exceeding, okay, the maximum concentration that you prepared, okay, to establish, the calibration graph. You prepare kosong di 500 ppm, okay, to establish the calibration graph. And then suddenly, I mean, the absorbance maybe from 0 to 1. Suddenly, the absorbance of your unknown exceeding 1.0, so maybe 1.2, for instance. Meaning it is beyond, the range of the concentration, okay, that we use. So in that case, okay, we call it extrapolation, okay. But extrapolation actually is not really encouraged, okay. It's not, we are not permitted, again, to do that, okay, because it's less ethic, okay, because we don't know what happened beyond the concentration that we study. Because interpolation, okay, we're talking about the concentration which is higher than what we prepared, okay, for the calibration. All right. So normally, actually, you are not allowed in analysis, okay, to the extrapolation. But sometimes, I mean, if you run, okay, many enough, the points, and then, if the relationship actually is a straight line, and then you can extrapolate much easier, okay, because you are having, you are having the what you call it, I mean, the expression, the formula, okay, for the straight line, okay. That's what I'm trying to say. Okay? All right. Okay. So I also want to know, okay, so look at the video again. Okay, so source here, the light source. What's the light source that we need to use? Okay. Okay, I put it this way. How many light source, okay, that we need to use, okay, in our lab? Sorry, in our instruments, okay. How many lamps, okay? How many light source, okay, that we need to use for the UV visible spectroscopy? Any guessing from you?
Just one.
Okay, Aswa, you want to try again?
1.
1. Okay. What's the type? What's the type of the sauce? Okay, that we use. Kalau satu tu apa nama dia? Sauce tu.
I'm not sure. Maksudnya yang kita pakai kat lab ke?
Yang kat lab ada berapa? Dia tak semestinya kat lab. Ada satu. Ada satu. You sure?
Light source tu bukan yang dalam spectrometer tu ke?
Yes. Ada satu. Are you sure ada satu?
I'm not sure now.
Okay, tak. Okay. What's the function of light source? What's the function of light source? If you can try, as far if you can guess. What is the function of light source? Or source of light? Light source is source of light, isn't it?
Yes.
Yeah, okay. What's the function of it?
From what I understand, the light will go through the sample and then it will give a reading.
Okay, give reading. How it give a reading? Dia kena kat sample dia bagi reading. What the phenomenon that involve?
What apa ayat ni?
Tak, okay. What happened? Okay, when you shown light, when you supply light, okay, into your sample, what's really happening actually? Okay, in the matter in your sample, what's really happening? Tahu tak? Tak, bila light source tu, okay, light source kena dekat your sample kan? Apa yang dia buat sebenarnya? Light source tu apa? What sort of interaction that occur between the light source and also, you know, the sample, the material. Tak apa, tanya orang lain. Okay, thank you very much, Aswa. So maybe can I have Muhammad Nur? Muhammad Nur, siapa ni? Muhammad Nur Syahir ke?
Ya, saya Doktor.
Alright, Muhammad Nur Syahir bin Muhammad Nur Azam. Ui. Nama ayah boleh makna, mana makna juga. Oh, ni double makna. Okay. So shall I call it Syahir or what?
Call me Syahir, Doktor.
Okay, Syahir. Apa yang berlaku bila light source tu kena dekat ni? Okay, once the light source actually, you know, been supplied, once the light been supplied, okay, by light source to the matter, okay, or to the analyte, what is really happening? Okay, what's really happening?
The sample tu will absorb the light.
Okay.
Then it will emit the light.
Dia ambil the
and
light.
give the wavelength.
Itu macam computer fluorescent lah sayang. Itu fluorescent. Okay, fluorescent tu dia bagi balik light. Kalau serapan ni tak bagi light, mana bagi light? So meaning, the light, okay, once you supply, you know, the light from the light source into the matter or into the what you call it, into the sample, the sample will absorb, okay, some of the light, and the remaining light will be transmitted to the detector. Okay, like from the video that you saw just now. The light will be received, okay, by the matter. Some of them will be absorbed, and they will undergo excitation. Okay. But the rest, okay, I mean will be transmitted, okay, to the detector. Okay, so we're having the light. A part of it will be absorbed, and some of it, okay, will be transmitted, okay, to the detector lah. Okay. Tak apa, ini tak nak buang masa sangat ni. Tadi pagi banyak sangat masa terbuang. Okay, but actually I want you to clear, you know, from the video. Alright. Okay, satu lagi monochromator. Okay, you see here monochromator from the video here, monochromator, and they have two slit, okay, one slit here, and they're having a prism. So my question is, what is monochromator? And why this monochromator is actually having kind of like relationship, you know, with these slits and the prism, the two slits and the prism. So we have one slit or slit one, slit two, and the prism. And no, I mean it's only component on only these three. Okay, so the question is, what is monochromator, and what's the relationship between monochromator and these three components? Okay, two slit and prism. Anybody want to guess? Muhammad Syukur Ilyas, maybe you want to try?
Yes, Doktor.
Okay, you answer me. You got the answers?
About what, Doktor?
Oh, ni tak pay attention ni. Tak pay attention.
Yang mana, Doktor? Saya ni.
Okay, monochromator. What is monochromator?
Monochromator.
And the relationship between monochromator and these two slit and prism. Okay, that's the question. What is monochromator and the relationship between monochromator and these three components here, two slit and one prism?
Monochromator ni kan macam dalam yang mesin tu, kan dia cahaya tu dia ditembak kan. Lepas tu dia akan contoh kalau visible dia warna jernih tu. Lepas tu dekat prism tu dia akan pecahkan dia punya warna tu. Jadi 7 warna. Lepas tu dekat apa nama satu gitu. Yang satu gitu dia akan terima satu cahaya je.
Satu cahaya saja. Yang mana anda yang ni ke? Yang mana?
Yang slit yang kedua tu.
Yang slit cuma satu cahaya saja. Maknanya cahaya dari sini ni, daripada light source, dia akan masuk ke sini ke?
Ya, so kena prism, cahaya tu dia akan...
Before that, yang slit satu ni dia akan terima semua cahaya ke macam mana?
Sebab dia akan terima satu cahaya sebab kan visible kan ada satu cahaya kan. Saya perasan dari satu cahaya putih, kena kat prism ni baru kena cahaya warna-warna. Macam tu lah.
Cahaya warna-warna. Lepas tu yang slit kedua ni?
Dia akan ada satu lubang tu, satu warna je yang akan melepasi satu lubang tu.
Macam mana dia pilih? Kalau nak tu ke? Kalau katakan sekarang ni warna kuning yang masuk kan?
Okay.
Kalau kita nak tukar kepada warna merah, macam mana nak buat?
Nak kata. Saya rasa memang apa kalau kena warna kuning tu, masa saya apa yang kena ni lah dekat lubang tu, kalau kena warna merah dia ni lah kot.
Macam nak bagi dia kena anak anda? Macam nak bagi dia kena? Tak, okey. Mula-mula kalau katakan kita kenakan di warna kuning kan. Okey, kita dah settle lah. Kuning dah masuk, semua kita dah detect, dah settle. And now kita nak tukar pula jadi warna biru. Macam mana nak buat? Apa yang kita nak kena alih kan? Ada nak alih apa-apa ke?
Oh, apa yang nak alih kan? Mungkin prism tu kot.
Prism macam mana?
Boleh set ke?
Oh, nak scan prism. Macam nak scan prism?
Mungkin
Doktor nak try?
Okey. Bagus. Group ni better sikit lah. Okey, anak anda sila. Siapa tadi? Aswagi ya?
Tak, Balkis.
Balkis. Okey, Fatinul Balkis orang. Okey, yes.
Boleh kata kecil slit dia tu. Faham tak?
Macam mana nak dia? Macam mana?
Slit kan ada yang celah dia tu kan. Boleh besar atau kecil kan. Sebab setiap warna kan ada wavelength berbeza kan. So slit tu kan ada benda tu, celahan dia tu boleh kecilkan atau besarkan ikut wave yang kita nak.
Betul. Contohnya lah kalau sekarang dia masuk kuning saja kan. Kuning saja. Kan? Kuning tu kat situ. Kalau anak dia nak tukar jadi biru yang masuk situ macam mana nak buat? Nak besarkan? Kalau besarkan kuning akan masuk juga kan. Betul tak? Kalau besar kecilkan slit. Kalau dia masuk sekarang dia kecil kuning saja. Kalau dia besarkan, dia kuning masih ada kat situ. Dia akan jadi besar tu, dia akan banyak lagi cahaya masuk.
Oh.
Yang mana agak-agak tu?
Ayahanda, what if kalau kita adjust dia punya prism dengan slit?
Bijak. Siapa ni? Siapa jawab tadi?
Saya Ayanda.
Izyan. Okay, tepuk tangan untuk Izyan. Okay, that's good. Okay. Right, okay, we need to adjust. Okay, dia punya slit, okay, dengan kita adjust dia punya prism lah, okay. Jadi once kita adjust, dia akan pusing macam tu lah kan. Dia akan pusing. Sebab tu monochromator ni kalau kita lihat kan dia akan bunyi, okay, because kita akan do the scanning. Bila buat scan tu macam dia scan wavelength, dia pilih. Kan? Dia kata monochromator tu tengah buat scanning. Nanti bila belajar UV nanti, dia belajar fluorescent. Macam fluorescent, dia akan ada dua monochromator. Kan? Satu excitation, satu emission. Tapi dalam UV ni ada satu saja untuk scanning. Sebab dalam fluorescent kita kena scan untuk excitation light dan kedua kita kena scan juga untuk emission light. Sebab tu dia ada dua. Yang ni dia ada satu. Okay, that's good juga Adit. Alright. Jenuh lah yang dia nak bagi hint-hint kat sana. Okay. Tapi maknanya, the reason I suka baca because you akan remember sampai bila-bila insyaAllah. Okay. Diteruskan. Okay. Tadi ayah ni dah tanya pasal light source ni kan. Ada berapa light source kan? Ya, okay. Tanya semula. Ada berapa light source ni yang akan digunakan dalam UV visible spectroscopy? Tapi tadi dia sebut kan, dia kata, okay, you can use, simple light, light, spotlight as light, light from the scooter, dia kata kan. Or you can use, more sophisticated light, like, dia sebut deuterium and tungsten, macam tu kan. Okay, jadi macam ada banyak, okay, light source sebenarnya yang kita boleh gunakan. So, hari ni nak tanya, okay, macam untuk biasa application dalam makmal kan. Okay, berapa light source yang diperlukan sebenarnya? Nak menjawab soalan itu, kena tahu, okay, actually we are working in the UV visible spectroscopy ni, okay, kita dealing dengan sumber cahaya apa ataupun electromagnetic radiation apa, okay, yang we deal with at the moment. Untuk UV visible spectroscopy ni, kita deal dengan EMR apa, okay, EMR tu electromagnetic radiation. So what sort of light that we are dealing with?
Deuterium.
Deuterium satu, okay.
Tungsten lamp.
Hebat. Okay, it's good. Big, it's a big round of applause, okay. Bagus ni you punya kumpulan ni. Okay, jadi dia malam ada dua. Kenapa dia ada dua anak anda? Kenapa dia ada dua?
Sebab satu nak detect
function
UV,
lamp tu
satu nak detect visible.
Somebody, Syaira mention apa tadi? Syaira kata?
Sebab function dua lamp tu lain-lain.
Okay, so apa function dia untuk dua-dua tu?
Kalau deuterium lamp untuk measure UV range. Kalau tungsten tu untuk visible light range.
Wow, okay. Betul ke ni Syukur? Tadi Syukur macam nak sebut something. Muhammad Syukur.
Betul.
Yeah.
Betul.
Wow, congratulations to both of them. Okay, it's good. Okay, jadi kita perlukan dua because of, okay, we need two range of light. Okay, satu dalam UV, okay, satu dalam visible. Kan, jadi kita kena dua. Jadi mula-mula bila buat scan mula-mula tu, dia akan tunjuklah UV tak sampailah 370, pop dia berhenti, dia akan naik pula yang visible. Tak sampailah 750 sampai 800. Okay, that's why they need dua. Okay, light source. And then what else? Alright, okay. So beam splitter. Apa guna beam splitter ni? Nanti anda tengok buka sikit, okay. Okay, ni cahaya sampai dekat sini. Okay, dia pilih kat sini warna kuning. Dia akan split into two. Soalan pertama. Untuk keperluan UV visible spectroscopy ni, berapa splitting diperlukan sebenarnya? 2 ke, 3 ke, 4 ke? Kan? Dan kenapa perlu untuk dia split? Okay, anak anda? Tak, kenapa perlu dia split? Kedua, actually how many splitting do we need? Okay, how many splitting do we need? You know, for our system. Any guessing?
Dua.
Dua. Siapa jawab ni tadi ni? Siapa jawab tadi? Tak perasan.
Saya yang ada.
Siapa nak dia? Tu cari, tak nampak. Siapa?
Daniel.
Ha?
Daniel.
Daniel. Awak tak clear kat sini. Okey Daniel, kenapa dua? Kenapa tidak tiga? Kenapa tidak empat? Jawapan betul lah tu.
Betul lah.
Kenapa tidak dua? Kenapa tidak tiga? Sorry. Kenapa tidak tiga atau kenapa tidak empat? Because the requirement only dua, okay? Because we just need, you know, the absorbent, okay, for the sample and for the reference. Reference tu sebenarnya adalah kita punya solvent, okay? Kita punya solvent. And okay, jadi bila kita ada absorbent untuk reference saja ataupun untuk solvent saja, plus absorbent untuk solvent plus sample, okay? So kita boleh dapat tak maknanya absorbent, you know, due to the presence of sample alone. Like in the experiment, okay, you are taking the absorbent for copper sulfate, and that copper sulfate actually you dissolve in distilled water, isn't it? So that's why, okay, your reference as is actually see the distilled water, and your sample is solution of copper sulfate. So the instrument is going to detect, you know, the absorbent of the distilled water alone, and then once you put your sample, the detector is going to detect, you know, the absorbent of the sample plus the presence of solvent. Okay. So in that regards, can we get, you know, the absorbent that's due to the presence of sample alone or due to the presence of copper sulfate alone? Can we do that? Boleh dapat tak? Kita ada reference. Macam mana, Daniel? Daniel?
Ya.
Dapat tak?
Tak.
Tak dapat? Dapat ke tak dapat? Boleh tak kita dapatkan? Tak dapat tak dapat Kenapa tak dapat? Okey, macam ni kan? Okey, macam ni. Ini adalah reference sahaja. Ini your solvent. Ini your solvent Your reference ni your solvent. Okay. Here actually your sample plus your solvent, isn't it? In here you are having your reference alone, which is your solvent alone, but here you are having your sample plus your solvent. So what we measure here in detector here actually the signal which due to the presence of solvent alone, but in the second detector actually what been detected here actually the signal, okay, due to the presence of sample plus solvent. Say we compare these two, do you think we are able, you know, to measure, you know, the signal that's due to the presence of the sample alone? Can we do that?
Kita push menggunakan masa boleh, doktor.
Yeah, okay, the answer is boleh. Okay, sebab tolakkan saja. Okay, because kat detector ni, okay, dia cuma signal daripada absorber saja kan. Yang ini signal untuk sample plus absorbent. Once you ambil ini total ni, tolak dengan ni, you akan dapat signal ataupun absorbent disebabkan oleh sampel sahaja. That's the thing. That's why we reference. Okay, kan anak-anak before you start your experiment, you need to do the zeroing, isn't it? You need to put your distilled water in there, and then you need to do, you know, the baseline. Okay, that baseline representing, you know, there is no signal. I mean, there is no signal due to the presence of the solvent alone. Dia dah zero siap-siap kan. Dia mungkin ada reading. Mula-mula masa you measure tu mungkin ada reading sikit. Contohnya mungkin ada reading 1 atau maybe 0.01 ke, we don't know. So very insignificant. Jadi untuk nak memudahkan, kita zerokan semua. Sebab tu that process sometimes the baseline process, okay, the process of getting the baseline from the reference, sometimes is called zeroing. Meaning you are defining, okay, to zero absorbance, okay, if what present actually the reference alone, I mean, or the solvent alone, alright. So that's your process. And then kenapa dia split? Okay, kenapa dia split dekat sini? Why they split it? Apalah dia split it, obviously satu supaya dapat satu beam. Okay, sample mana another beam actually to the sample. Okay. Jadi kalau kita gunakan, so meaning the beam splitter actually has been used, okay, to split the same beam from the same light source. Okay. So kalau katakan if you are not using the beam splitter, you might need, two same source. Okay, for instance, one source will go direct, okay, to the sample, the other source will go direct to the reference. But do we need to do that? Okay, the answer is no. Okay, we're not going to put two same or we're not going to put the two similar light source here, because using two instead of one, meaning, okay, you increase the cost, okay, of the instruments, okay, because you use two light source, and it's not economical some more, okay, because I mean the price could be expensive. Furthermore, the intensity could be different even though you are using, okay, the same light source. Okay, sometimes there will be some variation, okay, in terms of the intensity of the light, okay, that's been generated. Okay, but by using the same light source, okay, so basically you try to avoid, okay, the discrepancies in the reading due to the presence of error. Okay, jadi kalau guna satu ni, actually the same beam, okay, will be split into two. Okay. So actually it's going to give you less error, okay, in this case. Okay. Alright. Okay, mungkin satu lagi. Nampak tak anda kat sini? Okay, pada peringkat awal, we are putting solvent, and then sample pun kita letak solvent juga. And then we notice that the intensity of light, okay, that come out from the detector, it's more or less the same intensity, isn't it? Okay, slightly same. But once we increase, once we increase the concentration, okay. Kejap, dia buka ni.
100% transmittance.
Okay, kita tambahkan molekul.
Now notice that when I do this, the intensity of the light exiting the sample cell has decreased, and therefore the current generated by its detector has also decreased. So now the ratio of intensities is no longer 100%. In this case, let's say that it's down to 50% at a given concentration, which I'm going to call X. If I add another equivalent of my sample to the sample cell, that decreases the intensity even more.
So anda bila tambah lagi molekul, tadi satu, ni dua kan, dia makin kecil ni. Tambah tiga lagi dia kecil. Okay? Tambah tiga, mana tambah tiga je. Dia tambah tiga ni, almost hilang dah. Jadi kenapa? My question ni kenapa? Kenapa bila ditambah molekul?
Sebab dia
Kenapa anak anda, Balkis? Kenapa, Balkis? What's the reason for that? Sebab, tak dengar lah. Sebab
dia absorb light tu ke?
Okay. Sebab dia absorb light. Tapi macam mana bila molekul ada, tambah molekul dia absorb makin banyak ke macam mana?
Sebab dia banyak molekul, dia absorb banyak-banyak.
Okay, right. Kenapa bila banyak molekul dia boleh absorb banyak? Biar-Lamberts nanti akan tahu. Biar-Lamberts ni, in fact dalam makmal, Biar-Lamberts ni application only at very low concentration. Kan, disebut. Kan? Tapi bila banyak tu, okay, Kalau kita macam tadi, kita nak tambah molekul, dia akan, light tu akan, transmitted light will be less and less. So the reason we kata because of molekul bertambah. Macam mana molekul yang bertambah tu boleh menyebabkan serapan tu semakin banyak? Itu ayahnya tanya. Okay, any question? Any answer for that? What make molecule absorb light? Okay. Kenapa molekul boleh absorb light? Ada tak? Any guessing? Actually, we discussed about this last week. Kenapa molekul boleh absorb light? Adakah semua molekul boleh absorb light ke certain molekul saja? Ada nak tanya Izzah Jazilah. Okay. Izzah Jazilah binti Muhammad Zaki. Anak dia ada tak? Izzah Jazilah Muhammad Zaki 2.
Ada doktor.
Ada slownya. Mesti tak makan lagi ni kan? Izzah makan dah ke puasa ni?
Dah makan.
Ya, makan. Sebab puasa masih sempat lagi. Besok 30 Syawal. Okey, Izzah Jazilah. Apa soalan? Lupa tadi soalan. Soalannya apa tadi? Okay, what makes molecule able to absorb light? Okay, what make molecule able to absorb light? Apa yang menyebabkan molekul tu boleh menyerap tenaga? Okay, itu soalannya. What makes molecule, okay, absorb light? Izzah Jazilah. Ini sunatullah sebenarnya. Molekul boleh menyerap cahaya. Ini adalah satu sunatullah. Tapi Allah aturkan setiap molekul tu dia ada, okay, dia ada certain yang kita panggil sebagai chromophore, okay, yang boleh menyerap. Kalau tak ada tu, dia tak akan menyerap. Dan behavior dia berbeza dengan kalau dia ada. Jadi isunya apa yang menyebabkan molekul tu boleh menyerap? Anak dia? Izzah Jazilah.
Jadi elektron.
Jadi elektron? Molekul jadi elektron? Molekul jadi elektron ke maksudnya? Izzah?
Dan setiap molekul tu
ada elektron, lepas tu?
So dia absorb photon from light.
Okay, mana elektron dia kan absorb photon. Okay, jangan absorb photon. Okay, teruskan. Tapi tak semua molekul kan, betul tak? Tak semua molekul yang boleh menyerap kan. So, Jazilah punya expectation macam mana? You rasa semua molekul boleh menyerap foton ke ataupun satu molekul je boleh menyerap foton? Sorry?
Semua molekul.
Adakah semua molekul boleh menyerap foton? Soalannya.
Boleh.
Boleh? Okey. Okey. Macam tu ayah ada narrow downkan sikit. Adakah semua molekul boleh menyerap foton dalam jumlah UV dan visible?
Tak boleh.
Tak. Tak. Boleh ke tak? Kenapa tak? Kenapa tak? Apa sebab dia tak? Kenapa tak boleh pula? Kita kata ini adalah sunatullah kan. Allah jadikan setiap molekul itu berbeza daripada keupayaan dia, daripada sifat-sifat dia. So kita ni sebenarnya belajar sunatullah untuk molekul sebenarnya. Sunatullah untuk molekul. Masya-Allah. Ini Allah cipta molekul ni hebat ni. Okay, so setiap molekul akan behave differently. Jadi isunya adalah tidak semua molekul boleh menyerap julat UV dan juga visible. Tidak semua molekul. Kalau semua molekul boleh menyerap, so tak spesifik lah molekul tu kan. Maknanya semua sama je sifat-sifat dia ni kan molekul ni. Sebab semua dia boleh serap. Kalau semua molekul boleh serap, jadi kaedah tu jadi tidak selektif lah. Dia tidak jadi selektif. Dia boleh detect banyak molekul kan. Jadi kita nak kan kalau boleh, bila kita buat dia untuk detection ni, okay, they should be specified. Tapi isunya, apa yang menyebabkan molekul itu menyerap sebenarnya? Okay, apa yang menyebabkan molekul itu menyerap? Apa yang menyebabkan molekul ini boleh menyerap, molekul tak boleh menyerap? Okay, anak dia diberikan a group of molekul kat atas meja. Okay, macam ni kita nak tahu, oh yang ni menyerap, yang ni tak menyerap. Yang ni mungkin menyerap pada panjang gelombang lebih rendah. Macam tu. Macam kita nak tahu. Mana sekilas pandang, molekul kita tahulah dia boleh menyerap atau tidak. Okay, ada nak try? Tadi bagus dah, ni senyap je. Tak mengopi lagi ni. Meh mengopi dengan ayah anda. Petang-petang ni mengantuk sikit. Anak ada. So maknanya dia tidak semua. Mungkin Balkis nak cuba kot. Balkis, cuba Balkis. Kenapa molekul semua tak semua molekul boleh menyerap?
Sebab setiap molekul dia ada, macam mana dia punya excited state dia tu lah lain. So dia akan terima wavelength yang berbeza untuk dia absorb macam tu.
Quantize, okay? Maknanya setiap molekul dia having their own molecular energy, molecular level kan. Tapi yang lebih tepat lagi adalah yang dia, okay, setiap molekul tu dia ada molecular energy berbeza. Dan dia jadi macam tu kerana setiap molekul tu dia bina daripada atom yang berbeza dan ikatan juga berbeza. Atom berbeza, ikatan berbeza, menyebabkan environment tu juga berbeza. Kan? Jadi yang menyerap ni biasanya yang boleh, okay, yang menyerap ni biasanya adalah, yang boleh memberikan respon dalam julat UV dan visible ni adalah mereka yang boleh menyerap cahaya atau foton dalam julat UV dan julat visible. Dan ciri-cirinya adalah jeng. Okay. Satu adalah kita kena tengok, okay, sama ada dia mempunyai saturated bond ataupun unsaturated bond. Okay, kalau dia unsaturated bond, maknanya dia semua single bond macam tu kan. Saturated bond, mana dia semua single bond tu. Dia very unlikely, okay, untuk dia menyerap dalam julat UV dan visible sebab kalau dia sebenarnya adalah ikatan tunggal, tidak ada ikatan yang unsaturated. Elektron tu adalah elektron yang bentuk ikatan covalent yang sangat kuat, okay. Jadi cahaya UV dan cahaya UV dan visible yang kita bagi tu tak cukup kuat untuk nak mengeluarkan elektron tu untuk dia become excited. Jadi normally kita melihat molekul-molekul yang mempunyai elektron yang loose. Elektron tu dia boleh bobal, okay, dekat atas molekul itu, okay, dan dengan cara sebagai dia mobile, mudahlah kita nak tolak dia keluar. Contohnya kalau lah katakan kita nak menculik anak orang lah, contohkan anak orang ni. Kalau asyik ibu dia pegang dia kan kuat, dia susah lagi. Tapi kalau anak tu mungkin main ke ibu dia pun macam tak kisah sangat kan, anak tu mungkin main kat keliling ibu tu. Senang je kita ngap, kita tarik, kita bawa dia keluar kan, untuk kita culik dia. Contoh yang paling simple lah kot. So similarly, elektron macam tu juga elektron. Kalau dia terlibat dalam single bond ataupun saturated, okay, ikatan terpuk saturated, dia bentuk covalent bond. Jadi elektron tu agak sukar. Boleh dikeluarkan tapi perlukan tenaga yang lebih tinggi. Okay? UV visible tak cukup, okay, energi untuk nak keluarkan elektron tu untuk di-excite kan. Kita perlukan X-ray kot. X-ray dia lagi kuat, dia akan keluar insyaAllah. Jadi we are looking for molekul yang mempunyai double bond. Okay, double bond. double bond ke triple bond ke yang unsaturated. And then mungkin yang apa ni conjugation, okay, yang conjugation yang dia ada alternate, okay. Single bond, double bond, single bond, okay, double bond, single bond, itu alternate. Bila alternate ni dia akan memberikan satu kesan resonan. Kesan resonan tu elektron agak loose. Jadi agak mudah kita bagi tenaga sikit je elektron tu dah boleh serap dan dia akan terus, okay, melakukan pengujaan. Dia akan teruja. Alright? Itu reason dia. Dan satu lagi adalah bila kemungkinan, okay, yang pertama tadi adalah tengok tadilah yang unsaturated, the presence of unsaturated bond. Secondly adalah yang punyai atom-atom yang ada lone pair ni. Okay. Macam kumpulan halogen kan. Itu kadang dia ada dia mudah juga. Alright. Jadi hanya molekul tertentu saja yang boleh menyerap. Tidak semua molekul. Jadi kalau macam tu molekul-molekul yang boleh menyerap ni yang ada kumpulan apa ni unsaturated ni, jadi dialah boleh kita kaji dengan cahaya UV. Yang the rest tu kalau molekul tu memang tidak ada langsung, okay, double bond sebagai contoh, kita kaji dengan keadaan-keadaan yang lain lah, okay, untuk nak tahu dia punya karakteristik. Okey, jadi molekul tidak semuanya menyerap, okey, bergantung kepada chromophore. Okey, they call it chromophore yang ada di dalam molekul berkenaan. Okey, anak anda. So, I think kita dah kejap. 3:01. Anak nak berhenti sekejap ni. Tapi tak habis lagi ni, okey. Okay, sekejap. Right, okey. Ini, mana yang ini, okey, dia makin kurang ni sebab tu dah diserap, Sebab tu kalau kita tengok dia punya ratio tu semakin berkurangan. Ada apa-apa nak tanya tak anak anda untuk part ini? Do you have anything that you want me to clarify? Okey, anak anda sila. Macam mana?
Kan kalau apa tu tadi kan doktor kata split tu 2 je kan, satu untuk difference, satu lagi untuk sampel kan. Kenapa tak buat lebih? Maksudnya setiap sampel yang kita letak tu kita splitkan lagi. Maksudnya contoh kalau kita ada 4 sampel, kenapa tak buat split pada 5?
Tak, sebab reference tu satu. Ya. Tak, sebab reference untuk reference tu biasanya kalau kita buat calibration, we are still using the same reference, isn't it? We are still using the same solvent. Kita buat satu je, okay? Cuma dia kadang ada keperluan kalau kita nak detect, okay? Maybe we have a few sample and we want to detect them simultaneously, macam tu, kan? Contohnya lah itu you buat calibration, kan you masuk satu macam tu kan, betul tak? Tapi kemungkinan kalau you nak run, okay? Macam mana ada?
Kenapa tak letak serentak?
Tak possible. Ada alat yang modern sekarang ni memang dia boleh buat serentak. Maknanya dia punya sampel compartment tu mungkin ada lebih, tapi dia guna dipanggil sebagai apa ni diode array. Dia menggunakan diode array. Tapi ayah dia mungkin tak bincang dekat sini because I try to familiarize yourself with the basic concept. Jadi dengan diode array tu more on the detector. Jadi they can detect. Okay? Jadi they can detect. Tapi the splitting tu actually keperluan tu tak ada untuk lebih daripada 2, okay, atau lebih daripada 2. The most actually we just need 2 saja. Tapi does not hinder, okay, for us to detect simultaneously, okay, untuk kalau kita adakan mungkin sampel tu kita ada banyak. Okay, we can do that, okay, with special detector. But detector yang kita ada sekarang ni, kita guna photomultiplier tube. Okay, so satu detector saja. Okay, jadi kita alternately lah. Okay. Tapi tak kata alternate tak juga sebab what we doing, normally we just do the zeroing for the first time. Okay. After that, okay, we just introducing, the standard solution, okay, at different concentration. Okay. Dan normally dalam standard solution pun, actually we are not running 50, okay, for instance. Okay. Orang tak run sampai 15, okay, standard solution, okay, in order to establish, the calibration graph. Tak. The most maybe 5, 7. Kan 7 tu dah kira banyak lah. Jadi sebab tu kumpulan tu tak ada lah sebenarnya. Okay, kumpulan tidak ada. Berbanding kalau macam kita guna macam GCMS, okay, yang anda tengok hari tu. Okay. Jadi itu mungkin sampel tu memang banyak. Okay. Jadi sebab tu dia perlu kepada auto sampler macam tu lah. Okay. Tapi dah pergi jauh lah. Okay, tak apa, I stop there for a while. Okay. Okay, okay, so yang ni, ada tanya apa tak ni? Rasanya ni dah cover via Lambert. Rasa dah, kenapa dia convenient sikit sebab mudah untuk digaris lurus, okay, dan mudah untuk kita buat interpolation. So ada nak share sekejap, okay. Apa ni slide ni. Dan ini pun ada akan tebuk-tebuk je lah. Slide ni slide yang sama pada minggu lepas tu. Ini hopefully anak anda baca pasal kesan conjugation ni. Macam ni conjugation kan, tengok kesan dia akan move further. Mungkin ayah anda tak sempat untuk nak go through. Ya, tapi it's good okay for you to apa ni to read it and then just let me know. Actually conjugation ni sangat penting. Conjugation ni kena ada okay untuk, I mean the mulkus should have some sort of like conjugation okay in order to have, you know, very sensitive determination okay by using this method. Okay, another conventionally actually basically this the arrangement lah okay, this is the simplest arrangement okay that we have for the convex spectrophotometer, but we are not going to discuss about it. And this is actually the commercial that we have okay, the instrument that like we have in our lab. This is slightly different okay, the difference depending on the supplier. Okay, what we have in our lab actually tak silap adalah apa brand yang kita ada dekat dalam lab? Anybody remember about it? Okay, the brand of the UV visible spectrometer. Is it Mazu ke ataupun Perkin Elmer? Don't worry, it's okay. Tak masalah. Dia different brand. Okay, maybe sometimes the arrangement is slightly different. Okay, yeah, actually the compartment, sample compartment is here. Okay, and then you will see, you know, that the lamp, the mirrors, the prism, the detector is somewhere here. All right. That's maybe the spectrum. I think you're aware. Ini, you know, the setup, okay, for single beam, for double beam. This is the cell, and this is the flow cell. Okay, this is the flow cell. So they have a different type of cell depending on the application. This is the standard one, yang ini standard one. And you know the B here actually more or less is the same concept, but here, okay, we alter a bit in terms of the volume content. So volume tu dia agak terhad dekat sini. And here actually we can use like a flow through. Okay, so we build in the sensor here. And light source, okay, as been said just now, actually we have tungsten, you know, for the visible. We can hydrogen lamp or mercury lamp, okay, for the UV region. This on the spectrum. The prism does not, you know, the prism. Yeah. What I'm saying, okay, this actually, you know, I mean, this lead, what you call it, you know, the dispersion devices, okay, that we have. So we have, you know, like prism, and we also have grating. Grating has been made, you know, you know, a structure, okay, with smaller, okay, a shape of a prism here. So it's look like that we are having, you know, very efficient, what I call it, you know, the prism here, and this also is going to generate, you know, the first order of apa ni rainbow light, okay, and then the second order and so on, okay. So this can be also, I mean, this technology can also be what you call it. We can apply it, okay, in order for us, you know, to determine the sample simultaneously, okay. This is some of the concept okay, that been used. Okay, this is a prism here. We have polychromatic light or ray. What is the prism is going to be refracted, and you can see, okay, the infrared, the red, the orange color, yellow color, green yellow, and the slit is here. The slit is here. Okay, So once you want to select, you say want to select the rate. So you just need to move this above, okay? Or you can adjust the prism, okay? So that at one times only after, I don't know, after infrared, okay, and then maybe they can focus on red and then followed by orange, yellow, and so on. It's the party multiplier tube, okay, detector that's already been used, you know, as a detector. Okay, so the cost simple. Okay, so I think that's about all. Okay, this actually tadi ada anak dia tanya tadi kan. This basically, you know, the schematic diagram of photodiode array. Okay, this the array again that we use. Okay, more or less. Okay? Whereby it's going to allow us, you know, to do, you know, the simultaneous detection, you know, of various sample. Okay, so they are not doing the splitting. Okay, I want to highlight a bit. Okay, like been highlighting the videos, you know, the Beer-Lambert's law. Okay, so I'm supposed to finish, you know, anytime now. Okay, once you have a light coming and then the light out, this actually called transmitted light. All right, so you will have, you know, the Beer-Lambert here, the Beer-Lambert law, the relationship, like what you saw from the videos. And then we introduce, you know, absorbance, you know, as minus log T. So you simplify, okay, the expression. So A equal to epsilon BL. Right? And if you plot a graph, you know, you can have a curvature and then later on, okay, very straight line. And rating absorbance and transmittance is what been discussed, you know, in the video just now. Okay, you can see from here, you know, the exponential, and then you know the straight line. Okay, for the same video. Okay, basically, and one more thing, another you need to know that Beer-Lambert can only be used at lower concentration. Okay, you can see from the plot here, it's going to give you a straight line. Okay, but after some time, it's going to be plateau. Okay. Right. So the other thing actually we can only use, you know, Beer-Lambert, you know, at lower concentration. At higher concentration, not many molecule, okay, in that solution will be, I mean, will be exposed, okay, to the what you call it, okay, to the light, okay. So as a result, only the front liner or the front molecule that's going to absorb the light, but the rest again at the back here, basically there's nothing. Right. So another, I think that's about all. Okay, I think that I want to discuss. Okay, so I cover more or less, you know, regarding the UV, the instrumentation setup, and also, you know, the calibration. So here actually the example, you know, of the graph. We get the answer to them before. Okay, there is a sub A versus C where graph is linear. Okay, so like here. Okay, this, you know, the same method again, but using spatial probability analysis. Right. And this is an experiment that you did in the lab. Okay, a series of concentration and you plot a graph. Okay, and this actually the error versus, you know, the absorbance. So the percentage error is going to be very low. You know, if you're working more or less in the concentration range, again, they're going to give you about 0.5 absorbance. Okay, if possible, do not exceed 1.0. Okay, Ananda, thank you very much. This is an example of the previous soalan. Right, thank you. Any burning question that you want to ask, Ananda? Any burning question that you want to ask? Okay, penat dah 2 jam. Okay, if not, I will stop here. Okay, so hopefully I'll be able to see you again, okay, next week, inshallah. Okay, so we end the session, okay, by reciting apa ni, tasbih kifarah dan surah Wans. Bismillahirrahmanirrahim. Okay, anak dia. Assalamualaikum warahmatullahi wabarakatuh.